Alright everybody, welcome to the notes on Chapter 5, Section 6. This is the fundamental theorem of algebra. So we're going to use that theorem to solve polynomial equations with complex solutions. Alright. Big picture, the essential understanding right here that we need to make sure we have a good grasp on is that the degree of a polynomial equation tells you how many roots the equation has. And that's really all this whole fundamental theorem is about. It's very easy to see it graphically, that every polynomial of a function of degree 1 has a single zero, which is the x-intercept, okay? However, there appear to be three possibilities for polynomials of degree 2. When we look at this one appears to have two zeros, this one appears to have one, and this one appears to have none. Okay, so we're going to go a little bit deeper into that here. However, and we've done this, when we factor, we can see that each related equation has two roots. They might be complex, but the first one has two roots. The second one has two roots at 1. It's a multiplicity of 2. Okay, we talked about that double root. And then here it has two complex roots because we have I involved now. So every quadratic polynomial equation has two roots. Every cubic polynomial equation has three roots, and so on. This result is related to the fundamental theorem of algebra. Carl Friedrich Gauss, who lived in a very boring time with no TV or iPhone, is credited with proving the theorem. So basically all it works out to is that the degree of the polynomial tells you how many solutions there are. That's it. That's all we're looking at. So we can look at this one at the very beginning and know that, all right, x to the 5th, it should have 5 answers. And so we do synthetic division, and then we factor, and we keep going, and we end up with our 5 roots. So let's take a look at this one. What are all the roots of this equation here? So I'm going to walk you through how we would figure that out. So you're not going to do this one on your own. I'm going to walk you through it, okay? So first, we're going to get everything on one side, so we're going to set it equal to 0. That's not too hard. If you want to pause the video and try and work on this on your own and then catch up to me, that's fine. Then I noticed that there's an x on each term, right? So I noticed that I have an x here, obviously, here, and on the last term. So I factored out an x. So now I have this trinomial. Then I'm going to use synthetic division with x equals 1 as an answer. We'll talk about that more in depth in class, but I know that this has the number 1 as a root. Okay, and like I said, we'll talk about more about how I knew that in class. And so I do that, and now I have x squared plus 3x minus 10. Here I'm going to factor to get x plus 5 and x minus 2. So now we know that x also equals negative 5 and 2. So in the end, I have to go back to the beginning. Look, when I factored out an x right here, this now means that 0 is a factor, because 0 times this whole thing would be 0. So that works. 1 works because we did synthetic division and got no remainder. Then I factored and got 2 and negative 5. So my 4 roots for this quartic function are 0, 1, 2, and negative 5. Same stuff we've been doing. It's just that now that we are telling you can be certain that based on the degree of the function, we can be certain as to how many roots there are. We can use a graphing calculator to find any real roots. This is a really good way of doing this, and this helps with number 1. So I can graph this. I find the real roots at negative 3 and 3, and then I can just use synthetic division for the rest of the answer until I get down here, where I'm going to have to factor or use the quadratic formula. On this one, we used the quadratic formula. Whoa, hey now, slow down. All right, back up. So we used quadratic formula. We got these two, so our answers, our 4 answers here are negative 3, 3, and then this whole jumbled mess and this whole jumbled mess, okay? And so I know I'm done because those are the 4. So now what I'd like for you to do is, and you're going to use your graphing calculator to find the real roots, okay? And then you're going to use synthetic division or the quadratic formula or a combination of those two to find all the other roots. For part A, we're working with this equation right here, okay? You'll notice that we're missing the quadratic term, so you're going to have to put that in. For part B, I'd like you to work with this equation right here, okay? So go ahead and try and pause the video here, do A and B, and then I'll walk you through how I did those. Go ahead and pause the video now. All right, you've unpaused. Let's take a look at A. So first thing, we graphed it, and the real roots I got were negative 1 and 2. Okay, From there, I'm going to use -1 and do synthetic division, keeping in mind I put that 0 there for the quadratic placeholder. I get down to 2x cubed minus 5x squared plus 5x minus 6. Then I'm going to use 2. I'm going to use my other real root, and I'm going to synthetically divide again, and I get 2x squared minus x plus 3. Then I'm going to go ahead and use the quadratic formula. I plug all that in, and I get this mess right here, 1 plus or minus I squared root of 23 over 4. And so my roots are -1, 2, and 1 plus or minus I times the square root of 23 over 4. We have to remember that this is actually 2 answers, okay? If you want to be sure of it, I could write that out. The plus or minus is what makes it 2 answers. We've looked at this before and talked about how these are 2 separate numbers, but if you want, you could write 1 plus I radical 23 over 4 and 1 minus I radical 23 over 4. So there's our 4 answers for that quartic function. Part B is a little bit more complicated because it's a thinking question. So we're going to use this picture, use the turning points to explain why the graph does not show all the real zeros. Well, hopefully what you noticed is that this graph has a 5th root. Okay, or sorry, has a degree of 5. So we have, you can see we have a real root there and a real root there. We have these imaginary turning roots here of turning points. So we're gonna have something there. But then the issue becomes, where's the other root? So the function f of x is a quintic function with behavior of up, down. Because of this, I know that the view window is not big enough to see all of the real roots, and that the function, or functino, as I wrote right here, goodness gracious, will come back down at some point across the x-axis. So it's going to cross the x-axis again. It's not all here, okay, because of the 5th root. The other question says, part Roman numeral 2 here says the graph g of x equals f of x plus 4 is a translation of this graph. So we're just moving it, shifting it up 4. How many real zeros of g will the graph of g have, and explain? So it's quintic, so we know it has 5 roots. We can see that 2 of them are real, and there are 3 others of the remaining roots. Either there are 3 real roots or 1 real and 2 complex. Either way, there's at least 1 real root. There's at least 1 that does not appear as a real 0 in the graph. We can talk about this picture more in class, but really it's just, do we understand that even though it only has 2 roots here, there's another one that we can't see because of the nature of the function, because it's quintic. And then there's this in-between part where we don't know where these other roots are, these imaginary zeros. So, kind of a complex question. But not impossible in something that we can reason and figure out. Here's the fundamental theorem of algebra in more mathy terms, but it really is just saying the same thing we've been saying the whole time. If it's a quadratic function, it's got 2 roots, complex or real. If it's cubic, 3 roots, complex or real. Whatever the degree is, that's how many roots, that's how many zeros it has. All right, that's it for the notes, guys. Hopefully this made some sense, and we'll take some questions and go over this stuff in class. All right, see you next time.